a great honor to organize this conference. I mean, I'm in this field because I like it, obviously. I'm interested in it. And in particular, the first conference I went to this in Firenze, I believe, it stood completely it stood completely in a league of its own in the following way. I mean, in this field, there is a lot of conceptual issues, as you well know. And this conference, in my opinion, is the one where there was more sort of honest, real scientific discussion and less, I understand everything and I am the best, here is the work. It really hit me like this. So I really liked it and I tried to attend as many as I could. And this is a great pleasure to organize this here in Brazil. And Ana Julia.
So hello, everybody. Good morning. Welcome to Brazil. Welcome to São Paulo. So just as Giorgio said, it's a great pleasure to have you all here. I'm very happy to see, people from different groups merging today. So I was telling a few friends yesterday that a couple of years ago in China, when we offered Brazil to host this conference, I was the only Latin American there. And the years before, usually it's only Giorgio and I, and we thought that it's very productive to merge those groups, like who are doing different but very connected scientific work. So I'm very happy to see that it's happening right now. So have a great week, and let us start. Okay, so first we show very short videos to present you our many sponsors. So I think most of you know ICTP, and ICTP has been sponsoring conferences mainly at IFT, where most of you have been before. But this is Principia Institute, who also supported us in this event. So this nice place here is part of the institute that works here in the building in front of. So just very short videos for you to know them, and then we start with real scientific stuff. So thank you.
O Instituto Principia é um centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o You Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Yeah, we have 3 minutes before the first talk. So since we have people following us on Zoom, I guess we'll wait for 3 minutes. But yeah, mingle among each other. Why, as far as I know, no. Can you?
No desperate message yet.
This is the same as the because I don't have the timetable. Can you send me? Yeah, can you send me in the format that I can get, because I do not seem to be.
It's a good thing to me to come back in a place that I have done my PhD in an old IFT that was here now, to see this beautiful building. So I finished my PhD before this reconstruction. And okay, this is a work that I have done with my collaborators, and I took the liberty to spread this in 2 parts. Okay. So I'll talk a little bit about chiral vortical catalysis constrained by lattice LQCD, and I enjoy this meeting to show some recent results that we have obtained for chiral and the confinement phase transition when we introduce spin polarizer quark matter. Okay. So this first part is done in collaboration with my PhD student Rodrigo Nunes and William Tavares from UERJ and Varese, Salvador. And here, just a brief motivation. In the lunch yesterday, we was talking if it's in non-central Hawaiian collisions, we have the more perfect fluid or the more vortical one. So this is just some magnitudes of the angular velocity that we have, for example, for the Earth. And then when you find the QGP, this is some 20 orders of magnitude larger. So it's something that you think in radian per second is something really huge. And so how this thing that's rotated really fast with this intrinsic angular momentum can affect the physics of the QGP. In more particular, I'm interested in the phase transitions that happens in QCD, in chirosymmetry restoration and the confinement. So talk a little bit about rotation. It's one thing that is done, maybe the good paper since almost 10 years ago. And people do the approximation that we consider the matter produced as with strong approximations, that is, you consider as a rigid cylinder rotating with the constant angular velocity. And when you do this, you need to, for example, for preserve the number of fermions, you need to impose some boundaries on the border of the cylinder. And the results are really dependent on the boundary that you choose, can be MIT ones or another ones. And of course, if you go for this kind of symmetry, you need to change your metric for this one. That is correspond with this line element here that depends on this constant angular velocity. And another issue that you need to have in mind is that with a cylinder that there is a radio, and we need to obey always a condition that the angular velocity times the radio need to be smaller than 1, because we need to respect causality. So all these issues need to be done, already done in the game, and I will show you some results in a thing that I believe that is a puzzle on the game. Okay, this is a result that appeared in Chiral in 2016, when people implement rotation in an NGL model. When they have, for chirosymmetry restoration, they have a smooth crossover, and for some values of the angular velocity, they reach a critical endpoint. So the scenario here is the critical temperature for chirosymmetry restoration decrease when you increase the angular velocity. Okay? So this open a question. This is okay. It's what happens if you put here another axis on the phase diagram of QCD, when you can see if this huge rotation and how it can affect the scenario of the QCD phase diagram. So if there is real a critical endpoint here, and with the magnitudes that we expect from an experimental point of view and from simulations. So I I come to you with recent lattice results from this group. When I would like to call your attention here, they do this on the lattice, but this is for imaginary velocity, okay? So they do this for imaginary velocity, and for the small angular velocity, they do analytical continuation, come back to the real ones, okay? So here, this MPS is the ratio of pseudo-scalar mass of the vector 1 is 0.8. We know this is for heavy mesons, okay? And here we can see this capital omega here that they choose this capital omega for the angular velocity. We have degrees of freedom when we include gluons on the game or fermions on the game. So when you look for the critical temperature as against of imaginary velocity, when you have only fermions on the game, the result matches with the NGL calculation, okay? But when you put gluons on the game, the scenario is the opposite effect. When you put the two degrees of freedom on the game, the result is this red line that decrease. But pay attention that this is against the imaginary velocity. When you go to the real one, the behavior is opposite. So the lattice is saying that the critical temperature, in this case for looking for the Polyakov loop, for the susceptibility related to the Polyakov loop, is an increasing function of the angular velocity. So they have also results for the chiral symmetry, critical temperature, and the result is almost same. They don't have a splitting between these two transitions. And again, they have, for the same ratio here, they give us a result, a simple formula that it's the temperature a function of the linear velocity can be described by this simple equation here. And this coefficient B2 depends on the ratio of pseudo-scalar of the vector meson, okay? If you change that one, this coefficient will change. When you do the analytical continuation, we have this expression here that is a quadratic function of the linear velocity, the real one, okay? So if you look this, it's a puzzle that a lot of researchers are trying to put some new ideas, try to explain this. And to my knowledge, this needs to be solved because you have, until now, an open question here. So a rigorous QCD calculation is still necessary. And in my opinion, and some collaborators and friends, we believe that additional data from the lattices are most welcome to compare, okay? So the scenario is the lattice predicts the increasing of the temperatures, and the effective models the decreasing. So I will show some results here for a simple model because we are trying to understand the physics behind this. Just a 4-fermion model here with the free term here and a scalar and pseudo-scalar coupling. It's a non-renormalizable model that will depend on the scale at the end of the day. And you have 3 parameters that we adjust with the physical values for the pion mass, pion decay constant, and quark condensate. And we know that effective potential and for consequence, the gap equations are divergent. You need to choose a regularization scheme. But my point here is just try to see if you can change the models in some way to capture effects that we are not capturing now. So how we can do this? Because if you look for the lattice results, only the fermion degrees of freedom will have a decrease in critical temperature in agreement with that PRL that I showed in the beginning. But when we look for the effects of the gluons on the system, they are really dominant. So of course, these models, usually these models, effective models considered do not include, the gluons are not the degrees of freedom. For example, this model, this NGL model, there is no confinement. So one idea that you push here, how we can to mimic at least the gluon effects here. So we assume that it can be done if you assume that the interaction can be dependent on the angular velocity. So what would be the dependence? Okay, we use this lattice data as an input, let's say, okay? And try to see what the form that you have for the coupling. So this is the behavior. This equation is one that we choose. You can choose another one, but the coupling constant need to increase to capture that increase of the critical temperature. So one calculation more in QCD standard is most welcome to see what's the behavior, for example, of the alpha F of QCD with this guy. Can be an interesting problem on the game. As I said, we need to respect causality. So this one is one plot for a fixed radii of the cylinder. This is just 5 GV to -1. This is the parameter of the models that I'm using. This is the parameters that I use to fit the behavior that comes from the lattice for the critical temperature for chiral symmetry restoration and the confinement, for chiral symmetry restoration. Okay, what happens in the model when you assume this? This is the usual model with a fixed decoupling. When you increase the angular velocity, the inflection point here turns to the left. When we use that coupling that increase with the angular velocity, the inflection point go to the right by construction. So, and we have an increase at 0 temperature here for the quark condensate. And what happens with the quark condensate? This is an interesting point that comes from for the title of my talk that to for chiral vortical catalysis. Okay, the scenario is in the usual model. If you change the temperatures, okay, you have chiral symmetry restoration, but if you increase the angular velocity, you have this picture. But when we ask to the model describe to the behavior of the critical temperature of the lattice, what happens with the order parameter, with the quark condensate? This is that we calling chiral vortical catalysis. We have an increasing behavior of the quark condensate, okay? So this is some way, something that comes from the model when try to mimic gluons on the system. The quark condensate do not decrease anymore, but when you increase the angular velocity, he increase, okay? So this is the result from the lattice, and of course, this is our input. This is the behavior that we try to describe, forcing the model describe the lattice behavior, and this is the behavior that you have with the usual model. So if you believe that these lattice results are doing a good job, we have something that we need to take care and try to track properly, more formally in the theory, okay? So we have done an extrapolation here, okay? Because people have done this study in a lot of papers 10 years ago, and I tried to see what happens with the QCD phase diagram, temperature against chemical potential. So here I put the curves for the 0 angular velocity and 2 curves for the coupling that depends on omega and for the fixed decoupling here. I have done a zoom here to see if you, just to see the behavior of the critical endpoint here, okay? In the usual scenario, when you increase the angular velocity, we have a decreasing of the critical chemical potential and a decreasing behavior of the temperature. But when we force the coupling, we have the scenario is the opposite behavior. So the QCD phase diagram can feel this, the physics behind this, in our opinion, okay? So the running coupling enhances the chiral condensate as a function of the angular velocity. This we call chiral vortical catalysis, and I would like to be fair. The first guy that showed this chiral vortical catalysis was this guy in this paper here, okay? But he has a behavior there that do not describe this shaper of the lattice for the critical temperature. But the first guy to say, to come with this name in the model was this guy. As I said to you, I took the liberty to show some recent results that, in my opinion, it's one of the focus of this meeting, okay? That is related to spin polarized quark matter, okay? So this has been done in collaboration with William Tavares recently, and it will appear in archives this week. We are just finished some things, and I'd like to share with you and see your opinion and comments are most welcome, okay? So the spin, okay? In high energy physics, we have a lot of measurements, and when the spin, it's an important issue. We have the proton spin crisis. We can have single spin asymmetry and transverse polarization of hyperons. That's a lot of people trying to understand this. And the muon anomalous magnetic dipole moment, neutral electrical dipole moment. In Hevian collisions, you have a lot of phenomena with spin, and of course related and interacting together with a magnet field, and you have the chiral magnet effect, spin polarization, chiral separation effect, and between others. Okay? Spin is really a really important quantity in this game. Our motivation to try to simulate this in a model comes from recent lattice results from Sharon Dub and collaborators. Okay? When they study on the lattice the chiral and the confinement thermal transitions that find quark spin polarization. Okay? This spin polarization acting only in the quark degrees of freedom. So I would like not to be with a lot of equations here, but as this is something new to put in the model, I'd like to share just 2 slides with you. Okay? This quark spin density can be introduced via modification of direct Lagrangian like this one. Okay? Where this capital S here, it's a relativistic spin density matrix defined by this expression. This capital sigma mu nu is the usual one here. And if you assume the spin polarization along the z-axis, we choose the background spin field like this one. That is this guy in front. Where this mu sigma here will be the strength, okay? So there are some arbitraries in this choice. There is a recent PRL talking about pseudo-Gaussian transformations, but not my point here, okay? I'm just looking for this that people do on the lattice, and I try, I guess for the first time, try to put this in a model. And in this way, we can have this simple Lagrangian here with this sigma 1, 2 here that can be related to this one, gamma 3 and gamma 5 over 2, can be in this diagonal form, okay? So physically speaking about the problem, so this is spin potential. It needs to be clear, it's really similar to the chemical potential. But it's not a chemical potential because we do not have a conserver thing related to them. So this we call, and people on the lattice, in the original paper on the lattice call as a spin potential. Okay? So this is a cost of energy to add a spin 1 particle here, or a spin up down here with minus my sigma over 2. So therefore, this guy is defined by the difference. That's the imbalance in the system, and it's work beautiful as a thermodynamic parameter. So this is, if you come back now and look for rotation, okay? When you do rotation, the Lagrangian, it's something like that, where capital omega in their notation from the paper is the angular velocity. This term here is the orbital angular momentum term, and this is the spin term. If you close your eyes and ignore this guy that's really related to the rotation and think that this guy can be a mu sigma, this is the spin term. This Lagrangian shows us that it's a really good relation between spin and rotation, okay? This is the one point that I guess it's important to pay attention. Okay, what we have done recently, we took the Dirac equation related with this new term here, and after some algebra, that's not the point here, we obtained the dispersive relation for the problem. That's given by this. And if you see, the spin potential appears with an unusual contribution on the game in the dispersion relation. It's a shift here in this term. Okay, this pi part here is just pi 1 squared plus pi 2 squared. So the point is, taking now this dispersive relation in this context, looking for the spin polarization of the quarks now, the question is what happens for the chiral symmetry restoration and for the confinement phase transition. This is our question. Okay, so to do this, as we do not have on the lattice results a splitting between chiral symmetry restoration and the confinement, we choose the entangled PNGL model. It's a NGL model with a Polyakov loop that tries to simulate the confinement. And in this entanglement comes from the coupling depends on the expectation value of the Polyakov loop here. And this is why this choose, because the usual model without a spin, the transitions are, let's say, very close with no splitting between them. Similar to the lattice, okay? Just to do a game for the first time, in our knowledge, in a model. So this term here is the potential that we use to fit the pure gauge QCD at fine temperature with a log parameterization here, and the coefficients, of course, here depends only on the temperature, okay? And these parameters here are adjusted to .2 just to have these two transitions close one each other. As I told you, in this model, of course, we work in the simple mean field approximation, and this is the Polyakov loop potential, the term that comes to the mean field, the vacuum contribution, and the medium term, let's say, okay? But we cannot forget that this that I'm calling vacuum contribution in this model here, there is a dispersion relation inside there that depends explicitly on the spin potential, okay? So we take this one, build effective potential, and do the minimization to find the polar. At quark chemical potential in our results that I will show now will be 0, so the L dagger will be equal L, okay? We have two other parameters, the mass and the Polyakov loop. So let me show you the results that we have. This is the mass of the quarks against the temperature for 4 values of the spin potential. We can see clearly that we have a decreasing of the mass, and the inflection point comes to the left. And one thing that appears in our results is that if you increase the chemical potential, if you look with a bit of careful at 0 temperature, we have a jump here. And this geopolitical sign of first order phase transition that appear on the game caused by the high magnitude of the spin potential. So this is the behavior of the Polyakov loop. When you increase the magnitude of this spin potential, come to the left. So the critical temperature for the confinement is peaked of the inflection points of this curve. This is the criteria that we use. So just show you the susceptibilities that inflection points of that curves is clearly go to the left for the mass and clearly go to the left for the Polyakov loop. So the result that's coming here is that if you increase the spin potential, both temperatures decrease. Chiral symmetry restoration and deconfinement phase transition in this model at fine spin potential are decreasing functions of mu sigma. Okay, mu sigma is notation that people from the lattice use, and I keeping the notation. Okay, let's come back to the lattice results. Really recent, if it's from this year. So here it is, they are plotting by the imaginary mu I over pi t square in the critical temperature here. Here is for the deconfinement, here is for the chiral symmetry restoration, okay? For the ration of the pseudoscalar of the vector boson. And we can adjust by this simple function here. So they evaluate on the lattice this curvature here, okay? This curvature here is the inclination of this curve because it's a square here, and they have results for this guy. So here are plots when they are changing this ratio and looking for the peak of the susceptibilities, okay? This is a result that they plot in this paper also. And if you see, this is for heavy mesons. This is square. So if you take pi mass and 140 and whole mass and 770, this is square, it will be like 0.03 here. So if you take the lattice data for the heavy guys and do an extrapolation, it will be around 0.06, okay? And we have done the calculation of this curvature in the model. It's a factor half appear. It's 0.03. But I'm not saying that the simple model is the answer and this is the truth. But the lattice data is done with non-renormalized quantities. Okay, this depends of the lattice artifacts. So it's something that is normalized quark condensate of the lattice is not an issue. With rotation is much worse. So they claim that you can trust that you take for the unrenormalized quantities the peak of the susceptibilities. If you took renormalized one, the results doesn't change too much. Okay? So we have done this. We have a difference sitting here, but this, if you can see, it's extrapolation because the lattice regime is done for heavy mesons here, okay? So this is the phase diagram that you get. It's for the chiral transition, okay? We have a small crossover here if you increase the spin potential. As I told you, when you go to down in temperatures, you have that jump, and you have a first order phase transition here. This is really sharp, and we have a critical endpoint, okay? So this transition is happening with this strong spin potential. So why is also good work with spin potential? I agree with the arguments from that paper from the lattice. It's not necessarily cylindrical metric. We do not constrained by slow rotation. The slow rotation means that you go to high angular velocities, and homogeneous phases appear, you need to change the game. So no worries about boundary conditions, and causality violation is not a concern. It's already satisfied, okay? The conclusions of the second part is that the finite isospin density is introduced to quark spin potential in the canonical formulation of the spin operator. Again, it's not a chemical potential here because the spin operator doesn't commute with the Hamiltonian. And the recent results from LQCD and for entangled PNGL model show that chiral and the confinement phase transition are decreasing functions of the spin potential, okay? And we have a critical endpoint for these values here, okay? Just to finish, we are pushing forward. This is a renormalizable model, okay? Including also chiral symmetry in the confinement, but the renormalization seeding, because of this form here, is not a usual issue. We need to think how to treat this properly. So comments are most welcome. And we are trying to solve this one. And we are also pushing forward to see what happens with the meson masses if you change this guy, okay? And the inclusion of the baryonic density is to see what is the real role of the spin potential on KCD phase diagram. So this guy can affect a lot the KCD phase diagram, in my opinion, okay? So with this, thank you so much for your attention.
Questions? Yeah, first, Kenji.
Yeah, in fact, I have many questions, but just many comments, but just one question.
Okay.
So my question is, isn't it surprising to have such a big coupling constant effect as a function of omega? Omega is now about 100 MeV, right? If you see, for example, some counterpart of the magnetic field dependence, the magnetic field must be as strong as a GeV scale to have such sizable effect. But so it's really puzzling. How is it possible to have such a huge, big dependence? Right? So that must be coming from the gluonic sector, not quark sector, right?
Yeah, the behavior of the decreased temperature is from the lattice. You can say that it's majoritative from the gluons. Yeah, if you have only quark decrease, from the decrease, right?
Yeah, for example, the Victor Braguda did years ago the very nice simulation. I mean, the different introduction of the rotation velocity for the gluonic sector and the quark sector, and the quark sector is completely consistent with the chiral model, as you showed. That is the reason why the spin potential is completely consistent with the lattice. But then the gluonic part is a challenge. It is a real challenge. And your coupling constant dependence is a mimic, to mimic such as a gluonic effect. But my question is, what causes such a big dependence? That is a real challenge, real question. And that sensitivity is
really
even
huge.
more bigger than the magnetic sensitivity, magnetic dependence. So it's really surprising. So do you have any idea how is it possible?
No, I don't know how to justify physically that huge coupling that region. But as I told you, for me it's a puzzle how to treat the gluons and rotating system. Okay.
Thank you. Very nice works. I have a couple of questions, and probably later we should talk about this in more detail. But first, I was puzzled or curious, better to say. What is the physical picture that you have in mind when your quark condensate is increasing with the rotation? In my view, if you have, say, quark anti-quark bound system to mimic the quark condensate, rotation would sort of try to break them apart.
Yeah, but if you see the interaction increase.
Is that what you have in mind?
Yeah.
So, because they are,
Try to push forward, but the interaction between them increase.
Stronger.
Yeah.
I see.
This is the picture that I saw.
Okay. I was also puzzled by the huge increase that.
Yeah, it's huge.
Okay. And second, it was on the spin part. What I understand is that your spin density is mimicking the effect of rotation in this cylindrical geometry, which
Not
is difficult.
necessarily this, let's say, to
Right.
polarize.
But one thing should hide the other thing. So in other words, the problems that you have when you have this cylindrical geometry, which you mentioned, should also be hidden here somewhere, because it's not, there's no free lunch. So where are they? Do you have an idea?
We have, when you do rotation, we have these two effects properly separated, okay? The orbital angular momentum one and the spin one, clearly, okay? If you just neglected that one, you can say that they are really entangling, let's say, okay? So to answer your question, if these arbitrariness and dependence are sitting here in something, I don't know. I'm just saying that you can have polarized matter without including and putting explicitly that orbital angular momentum on the game. That avoid this kind of stuff. This is the point. Because we know that from the experimental point of view, we have polarized matter. The question is necessary to put this in looking for the orbital moment. You can reach the same interpretation looking for a different quantity sometimes. This is the thing. But we are working this recently, so I do not know if I have the physical picture clear understand. People are doing and put this forward really recent. Kenji will be in a few days with spin hydro stuff. So I'm an equilibrium guy and looking for just trying to understand physically how you can have quark matter polarized, because you know that the matter is polarized. Okay, this is the thing. But we can talk about this.
Yeah, I just have a very brief comment coming back to what Kenji asked. So you are playing the very same game as with the magnetic field, that you make the coupling constant dependent on omega. And in this case, it's quite different because the gluons feel the rotation themselves and not just through the fermions like it was in the case of the magnetic field. So it's quite different. And I think it's, as you said, it's important to check this on the lattice and do a systematic analysis of it. And I suspect that renormalization is more complicated in this case. And one has to be very careful about that. But thank you for the talk.
Okay.
Thanks to the organizer for having me here. It's very nice to be back in Brazil. And today I would like to talk to you about some work we did in collaboration with Eduardo Grossi and Ismail Zahed about the spin alignment of the phi vector meson in the hadronic phase of the Quark Gluon Plasma. But as I realized, maybe not all of you are very familiar with this kind of polarization phenomena. I just like to start with a very brief introductory slide about what we are talking about. So, and why we are interested in this. So the main reason, I guess, at least for me, why we're interested in this is because there is some polarization effect that is observed experimentally. So people measure the distribution of lambda particles, and they see that there is some preference in the direction of the spin of this lambda. And in this case, we have, we talk about spin vector polarization. You know, lambda is a spin 1/2 particle. The spin can either be up or down, so you don't have that much freedom. And in this case, for the spin vector polarization, we have a model based on hydrodynamics that tells us that how basically this particle would be polarized. And I chose basically to show this picture because from this picture really we can make the point why we think that this effect is driven by hydrodynamics. So first of all, you can see that lambdas and anti-lambdas are polarized in basically in the same way. So like effects coming from a charge odd interaction, let's say, would be the opposite way. And also here we also have some data for the cascade and the omega particles. So these other two particles also are polarized in a way which is consistent with what we observed from the lambda. So these effects seem to be kind of, let's say, quote unquote, universal. So it doesn't depend that much on the particle you consider, and this hydrodynamic model works relatively well for all particles. And then we have another polarization effect, which is the spin alignment, and this is the topic of my presentation. And this is a tensor kind of polarization. Now the phi meson, like the K star here in the picture, and also like the J psi, the rho, and there are many particles for which this effect is observed, is a spin 1 particle. So you have 3 possibilities for your spin, and this kind of detail, in fact, is enough for you to have a much richer structure of what of the polarization effects you can observe. And this spin alignment, in fact, is a spin tensor polarization, not a spin vector. This rho 0, 0 is a component of a sort of a spin density matrix, so you basically try to organize the probability of having your particle polarized. And what people can measure is this basically the longitudinal components, like for this polarization. Now, this plot, which comes from a 2023 Nature paper by Starr, shows 2 things, which we can already see some difference compared to the lambda polarization. So we have 2 particles here, the phi and the K star. They're both spin 1, so they both can have this tensor polarization. But there is a difference. So the phi, we can see there is some signal which is significantly different than from the baseline. Now here the baseline is 1/3, which means simply that there is equal probability for the particle to be polarized up, 0, or down, let's say. And this phi meson has a significant polarization, especially at low energy, whereas the K star doesn't really show any significant polarization. So this effect seems to be dependent from the particle you observe. There are also other measurements about J psi and rho, and they're all like, I mean, they're not completely, there are different behavior for these particles, even though the measurements are sometimes in different kinematical regions, so it's hard also to compare. But yeah, so there's that. So maybe this phenomenon is not entirely driven by hydrodynamics. And in fact, the leading theoretical model we have to describe this spin alignment, at least for the phi, was developed by Xin Li and collaborators in this series of papers, and is based, in fact, on the idea that there is some intermediate strong field that fluctuates, polarizes the strange quarks that then end up building the phi, and then from this strong field fluctuation you get the final alignment of the particles. And in this model, what happens is, since one doesn't know in principle these fluctuations of the strong field, they use the global spin alignment data here to fit to determine how large these fluctuations are. And then using this fitted data, they are able actually to describe very well the momentum dependence of this spin alignment. And they were also able to predict, in fact, the rapidity dependence of the spin alignment in a later star measurement. However, I have to say, so this model works very well. However, there is still this kind of, it seems to me at least, we are kind of trapped in a loop, because we are, at least up to now, using alignment data to explain the alignment data itself. So, I mean, it would be desirable to have first principle calculations. I have to say that this group is working on that. Lucia Oliva presented some results in Quark Matter 2025, so I'm really looking forward to see the progress in this. And also in these simulations, like the hydrodynamics of the QGP, that still we know is there. The hydrodynamics works very well to describe the QGP. It's not really taken a lot into account. So this is basically what motivated us to try basically to follow a similar path and try to compute from a first principle how the phi would be polarized in the hadronic phase of the Quark Gluon plasma by some interactions with kaons, mainly, basically. And then to test the model first in a Bjorken regime, and then trying to put up some real hydrodynamic simulation and see what happens to our models. So this is some result we have from Bjorken. We have a small effect, so this from the 200 GeV step data. And then to see the real final result, you will have to wait till the end of the talk. So now let me start basically to explain how we did this calculation. So first of all, the phi emission rate can be computed in a similar way as you would do with electromagnetics rate. You have the number of produced phi, depends on some Boltzmann weight and phase space volume, but then the important thing is this amplitude between an initial state with no phi and a final state with a phi. And you also have to specify some scattering matrix, of course. And here we use basically the same interaction also as Xin Li uses between a phi field and some strange current, where we have some coupling G here. Then basically you do the calculation, you define the phi state like this. This is just to define what is the decay constant of the phi, and you have also polarization vector here. And in the end, you can rewrite the rate in this form, where aside from this Fermi-Dirac distribution, couplings, and so on, the important player in what the calculation will be is the Feynman propagator for this phi. It's a thermal propagator. And I remind you that this is the definition, so it's just a time order product of the two-point function in a thermal medium. So basically, once we have computed this Feynman propagator, one has the rate, and from the rate one can compute the number of phi, and then from there whoop, this is too much. Oh no, this is good. From there we compute the alignment. Now to compute this Feynman propagator, we use an approach that was also used in this paper here. Basically, to compute this trace on a thermal state, one can organize this trace by basically developing the trace in the most abundant states you have in your system. So instead of having all of them, you just consider the states that are more abundant. And to do this, basically, we want to deal with phi mesons, so we know that kaon states will be important because there are strange quarks in kaons. And also we also included some nucleon states or baryonic states, because as I mentioned in the beginning, we are interested also in maybe since there is a higher polarization in this low energy section here of this plot, maybe the baryon density plays an important role here. So we also include nucleons. And this is how the expansion is set up. You have the first contribution come simply from the vacuum, and then you have some kaon spectral function here, which is weighted by the kaon density. And then we also some nucleon spectral function weighted by the nucleon density. And in principle, this continues, but we truncate this expansion at this level. And now the only thing that is left to do is to compute every single term and then add them up. The first one, of course, is the simple one. This is just the definition, basically, of the phi meson spectral function. And once you have this term here, you can put it back in the rate, and this is the rate of phi that you obtain. But this, of course, since, as you may expect, the easiest thing is not the really important one, because as you can see here, the rate is isotropic. So this delta here tells us that regardless the spin of your phi, you end up getting the same rates. So, but this gives me the opportunity also to show you how we define this spin density matrix. So it's just the number. So this is the number of particles with a given QT in the longitudinal state of spin divided by the total number of particles emitted. And indeed, since this guy here is isotropic in spin, when you compute this, you can see that you get 1/3. So this first contribution is just the baseline for our polarization effect. So after this comes the important part. So I will not give too much details on this, but like we used formalism developed by Zahed and Yamagishi in the 95, I think, and then extended by Kamano in the 2010. And this is a formalism to address like chiral symmetry breaking, in principle. Like this was developed really for SU2 chiral symmetry, and then Kamano extended for SU3. And it's basically a different approach compared to chiral effective theory. It's based on some algebraic properties of the currents that generate the symmetries. And I will not say anything further than this. But basically, the idea is that with this formalism, one can compute the spectral function in a K-on state in terms of the vacuum spectral functions of of some other vacuum spectral functions. So this is what we did, and these are the results. So there are a bunch of spectral functions appearing here, not entirely important. But in the end, this is the rate we have. So as I said, there is still this K-on density here. And then in each of these spectral functions, there is a 1 over fk. This is the decay constant of the K-on. So the effective kind of expansion parameter here is this K-on diluteness, which, as you can see, is a very small number. So like this tells us that this expansion you are doing makes sense in a way. So like this correction here will be suppressed compared to the leading term, but it's still there. And then we get like these non-trivial dependencies on the polarization of the phi. So this will be giving us the spin-dependent part of the rate. We can also, from here, we can also compute dissipative correction to this. Now, this is done in I would say, in a Zubarev-like fashion. I think there are probably better ways to do it. I think Daniele is going to discuss about it later. But the idea is similar. So like we have some density operator that we expand in terms of the gradients of the temperature field. And then the 2-point function between currents is just the leading term plus gradient correction to it. This is just in 2 lines what the idea is. And this is the result which we obtain. There are still spectral functions around. And then the dissipative corrections are, of course, modeled by these shear and expansion terms, where the transport coefficients of shear and bulk viscosity appear. Basically, in this case, they appear as an estimate for some relevant interaction timescales. But anyway, so this is also the dissipative correction we include. And once we have done this, once we have done this calculation, the first thing we wanted to see is to test this calculation in a toy model. So we took like a standard Bjorken flow and computed the integrals there to see just if the effect exists, can do something. And indeed, we can see there is some small effect. This is enhanced if you put your K-ons like out of equilibrium, putting some K-on chemical potential there. But still remains kind of a small effect. Here the data are more or less described. This is, as I said, like these are data for the 200 GeV collisions, but basically there is not really any spin alignment in these collisions. But anyway, there is some effect. So this motivated us to go further, see if we can put some realistic hydrodynamic there, and also if we can maybe try to describe the low energy data with the inclusion of this interaction with nucleus. So we chose to model the interaction between nucleus and the phi meson with this Lagrangian. We have some Dirac term and the Pauli term here. And again, without going too much in the detail, because it's kind of an involved calculation, the important thing to mention is that the rate is modified like this. There are 2 players here. This function, this f, that comes with an isotropic rate. And then we have a g, which would give us an anisotropy in this emission. However, it seems already from kinematic consideration, this f would be probably dominant over the g, because this is always present, like for stable and unstable particles, both in the S and U channel, whereas the g is only present like for unstable particles in the S channel, and in the U channel it's there, but it's kind of it's kind of small. Anyway, we included this, and as hadronic states, we consider protons, neutrons, and and as a baryonic state, we consider proton nuisance and resonances. And now comes, let's say, the real part, where we attempted to put some hydrodynamics here. So when I submitted this abstract, I hoped to show you some definitive results. This is still preliminary for a number of, let's say, contingent reasons, but yeah, I don't expect the conclusions to change dramatically. So to tell you what we did, basically we set up hydrodynamic code. This is Fluidum, developed by Edoardo Grossi. And we use some realistic initial conditions, some Trento initial condition, but we use some 2+1 dimensional hydrodynamics. Then we have this fluid dynamic code set up, which shows some temperature range where we think the hadronic phase would be kind of reasonably applicable. And this temperature range has been chosen between 110 and 170 MeV. And then from here, basically, we have our hydrodynamic evolution, we have our formula for the emission rate, and we just integrate them along the hydrodynamic evolutions. These are complicated integrals. There are up to 9-dimensional integrals, so we did use some Monte Carlo methods to do that. And this is the part where maybe we can improve a bit. And then we still have some free parameter in our model, but in this case we can, since this is just the emission rate of phi, so that you can just fix these free parameters to some other observables, such as the phi spectra observed in experiments. And once you have fixed these parameters, you are done, and then you can try to really predict what's the alignment from the model. And so here it comes, and it doesn't really work. So what I'm showing here is the data for recorded by star for out-of-plane alignment. So this means that you take the quantization axis of the phi meson in the y direction, so in the global angular momentum direction, and then you have the in-plane alignment is when you take the quantization axis in the longitudinal direction. So the in-plane, more or less, one could maybe claim qualitatively is described, but since the effect is basically consistent with the baseline, so there is not really any spin alignment, I wouldn't claim that this is like a big breakthrough. And the out-of-plane spin alignment is really not well described. We predict some negative spin alignment. Now, again, this preliminary, but I mean, unless we find out some minus sign that has been missed somehow, which I don't think, then this probably will stay. We can also consider the local spin alignment. Of course, we didn't describe the global one, so we cannot expect to describe the local one. There are some features that we find consistently, so some negative alignment in the low momentum region, and then some peak, which is connected to the peaks in these spectral functions. But I mean, it's clearly not working. Then, just to conclude, I just want to discuss the contribution from each of the terms considered. And as it turns out, what is dominating this kind of physics, at least in our model, is really the interaction with kaons. So the total alignment follows this interaction very closely. Viscous corrections are just some small correction at low PT. And then, kind of surprisingly, this nucleon interaction really plays no role at all. So we played with both with the chemical potentials. So we played a bit like we started from the experimentally estimated chemical potential, and then we tried to increase, put some Bjorken scaling, pretty constant, but nothing really happened. Also cranked this coupling constant to see what happens, but this, unless like the coupling constant are really astronomically large, this effect really doesn't appear. And yeah, with that basically I conclude. Maybe I don't know if I'm ahead of time, but anyway. So what we did is we included, we tried to compute this phi fluctuations, let's say, from this effective, from this chiral master formula approach to describe this flavor symmetry breaking. And then on top of that, we use the 2+1 hydrodynamic code to compute the emission rate, and we also included interaction with nucleons, but we found the effect to be negligible. So our model, as I said, doesn't really describe the data. This may be for a series of reasons. So for instance, like maybe the chiral symmetry is not really a credible starting point to describe like also kaons, but in that case one could try to describe the raw meson spin alignment. In that case maybe the formalism should be more accurate, and maybe one has more success. But also the other reason could be that since we are in this case considering a boost invariant fluid, maybe we are not describing the out of plane spin alignment simply because there is this boost symmetry. And maybe so there is a need for 3+1 D hydrodynamic simulation, but if that is the case, I think that would be really like very expensive at the computational level, because you really have to track the evolution of the fluid at each time step, so you have to save the full 3D grid, so it becomes really, well, it becomes heavy. Probably can be done, but really, really heavy. And with this, I conclude, and thank you for the attention.
Thank you. Thank you very much. Actually, also finished early, so there is time for questions. Sure. Lynn?
Thank you for a very nice talk. So I'm trying to understand the origin of your effect. So I mean, basically you are computing the current correlator for phi.
Exactly.
So if phi is static with the medium, I would expect the current correlator to be isotropic, meaning that it's proportional to delta ij. In that case, there shouldn't be any spin alignment.
If phi is static with the medium,
if unless the phi is moving with respect to the medium, then the self-energy, the current correlator becomes anisotropic. So
this comes really from. So this is basically the current correlator. This comes from this approach developed by Zahed. Maybe we can try to talk a bit offline. I'm also not an expert about this, but like this is the result of the calculation. So basically, this master formula comes from basically really like algebraic relations between currents and how states are defined. So in the end, with this kind of machinery, at least, so this calculation was done by Ismail, and he's able basically to express this in terms of vacuum spectral functions. So there is some momentum dependence here. The I think the non-isotropicity comes from the fact, really from like this. So you have. Let me see. No, where was it? Next one. Yeah, so you have this. And then you have some momentum integral. So when this becomes proportional to k mu, then the product with this polarization vector is non-zero. So in our model, the anisotropicity comes from there. So like there are some, in this spectral function, there are parts that are proportional to the momentum of the kaon. And then when you contract them with the polarization of the phi, which has a different momentum, then you get non-zero. That's really this sort of an algebraic way to put it. Then I don't know, but we can discuss probably.
Okay. Thank you.
Andrew, very nice talk.
Hi.
I actually have a similar question to Shu. I'm trying to search for the origin of this contribution. You said is based on the kaon status, but the phi, unlike the rho or k star, which they have decay and then regenerate. For phi, it decays into kaon, right? Once it decays to kaon, the parent is gone. I don't understand why the kaon states will have anything to do with its parent
with them
production imbalance in different states.
Could you repeat? You don't understand why the kaon?
So on this slide, it says the most relevant on kaon states, right?
Yeah.
But once the phi decays into kaon, the parent is gone. And so I don't understand why the Kayan's spectral function has anything to do with parent production, the imbalance of the parent production in different states.
The imbalance of phi production in different states, you mean? I'm not sure if I understood the question, but like, so you're saying the phi decays to kaons?
Right, the phi decays into kaons, right? Once it decays, the parent is gone.
Yeah. No,
so whatever the daughter behave,
so I think this is a way to basically, in fact, describe that this. So there are like we have, I think, in mind this hadron gas picture. So there are phis and k's and k's as well, and so like it's a way to model, I think, this kind of interaction between phis and k's. It's not really like a decay. We don't describe the decay here.
Okay, I'll talk to you afterwards.
Okay.
Further questions? If not, thank you very, very much for and now an announcement from
So